Good evening, dear friends. In this video, I am privileged to give the complete information pertaining to finite difference method in the course Computational Fluid Dynamics. Anyhow, in the previous videos, I could give information pertaining to introduction to computational fluid dynamics, the pertinent governing equations used in CFD, next introduction to one-dimensional and two-dimensional Euler equations, then representation of functions on computer, finite volume method. But in this video, let me take the initiative in covering a few very prominent topics in a finite difference method, which is exclusively for undergraduate students. Friends, you know that in computational fluid dynamics, there is a particular technique called discretization. What exactly is this discretization? Discretization is the process of converting ordinary or partial differential equations into simpler form of algebraic equations. But you will question, are there any particular discretization methods in computational fluid dynamics? Friends, the answer is yes. Anyhow, in the previous video, I could give information about finite volume method. But today, we shall take up finite difference method. What is this actually? You all know that there are three prominent discretization methods, namely finite difference, finite element, and finite volume. But we shall know very comprehensively about finite difference method. Anyhow, in this particular video, we can give the information in a very concise manner, but very comprehensively we require maximum duration for that. Why? Because finite difference method is itself bigger than an ocean. Okay, so what exactly is this finite difference method? What are all the pertinent topics to be learned in the undergraduate level? Let me tell. Initially, one should be aware of the definition for finite difference method. Then you should be aware of the relevance of Laplace equation, Burger's equation, next convection diffusion equation. You should be aware of requirement for implicit and explicit methods, the different forms in convection diffusion equation. Next, very important, we should be aware of Gauss-Seidel method followed by Jacobi's iterative method. Next, a very typical concept called successive over relaxation. Next, you should be aware of tridiagonal matrix algorithm. Finally, you should be aware of a few schemes in finite difference, and eventually you should be aware about von Neumann stability criterion or stability analysis. Let me give the information in a epigrammatic way. Each and every topic is very important. Whichever is very relevant for undergraduate students, let me emphasize that. Initially, what is this finite difference method? Friends, this is one of the oldest discretization methods what we know. It is believed that one of the very famous mathematician and physicist, Leonhard Euler, developed this discretization technique somewhere in 1768. So from 1768 till date, this discretization technique is regarded as a very supreme one or a paramount one. What exactly is the idea? Friends, you all know that in the numerical techniques, whatever the students have learnt in engineering mathematics, they have come across forward differencing, backward differencing, central differencing. Okay, so those three are very important in learning engineering mathematics. Whatever forms they have learnt in engineering mathematics while learning numerical techniques, the same is applicable in computational fluid dynamics. Anyhow, in the previous videos, I have strongly emphasized that whatever mathematical versions of partial differential equations earlier in the first and second year curriculum of engineering students have come across, it has the extension or relevance to computational heat transfer and fluid flow. So here also, to know the comprehensive understanding about finite difference method, one should be clear about the grid system, the depiction of elements, nodes in that grid system. So please be aware that you should be clearly aware of the representation of nodes in a grid system. What exactly is the idea? Very simple. You know that in a grid we can represent 4 quadrants. Okay. In that we can take up 2 nodes, I comma j. So in each and every point or location we have to depict the nodes properly. When we write I comma j in the beginning, next it will become I comma j plus 1. To this side we can write I comma j minus 1. Likewise we can write I plus 1 comma j, I minus 1 comma j. We can depict the nodes in all prominent locations in a particular grid. Later on, by using finite difference schemes, we can comfortably write the equations for forward differencing, backward differencing, central differencing. These three one should be aware of. Okay, so this is the requirement or need for finite difference method. Alright, after knowing some introduction about finite difference method, what is the next idea? Friends, you should be aware about the relevance of Laplace equation. Have you not written Laplace equation while learning engineering mathematics? Yes. Fourier transformation, Laplace transformation. So few forms in partial differential equation, they are all very prevalent in learning computational fluid dynamics. So friends, you should be clearly aware about that. Alright, in one of my videos, I have clearly explained about the classification of partial differential equations. What are the 3 basic forms? One is the parabolic equation, second one hyperbolic, third one, it is very evident, elliptic. Okay. So, to know about the prominence of Laplace equation, you should be clearly aware about the categorization of partial differential equations. Okay. Therefore, what we can do, we can connect or correlate the PDE with Laplace equations. I have already explained in one of the videos, you know the form of quadratic equation. In that, what is the discriminant? B square minus 4ac. Okay, you all know that. If b square minus 4ac is equal to 0, what do we call that form as? It is parabolic equation. If b square minus 4ac is greater than 0, what do we call that as? It is hyperbolic. When b square minus 4ac less than 0, evidently what is that? It is elliptic form. Okay, so this is what we learn in the relevance of Laplace equation. Okay, so initially we could know about the introductory remark to finite difference method. Next, relevance of Laplace equation. What is the next one? Friends, while learning conventional heat transfer, have you not come across one of the modes of heat transfer, convection? Yes, you are aware of. But while learning computational fluid dynamics, we don't just deal with convection. Along with convection, we deal with what? Diffusion. So, what is the next form of equation? Convection diffusion equation. This is very important. The amalgamation or combination of what? The two heat transfer processes, convection and diffusion. What exactly the relevance of this? What is the exact mathematical form, friends? When we furnish convection diffusion equation, we will involve with velocity factor. We will involve with the divergence factor. We will entangle with the diffusion coefficient. So, when we combine all these mathematical terms, it will lead to what? The structuring of convection diffusion equation. Okay, please bear in mind, convection diffusion equation is the combination of both hyperbolic and parabolic partial differential equations. This may be an esoteric idea for the undergraduate students, but when they understand the quintessence of each and every equation, learning in the advanced level will be easy for them. Alright? Okay. So after knowing about convection diffusion equation, what is the next form? It is Burger's equation. Friends, while learning mathematics, have you not come across Burger's vector? Very analogously in a finite difference scheme, we will come across what? Burger's vector. Okay? What is this actually? Burger's vector is a form of representing partial differential equations. Okay? We all know that ordinary or partial differential equation should be discretized to obtain what? Linear algebraic solution. Initially, while writing any form of mathematical equation in CFD, please bear in mind it will be very cumbersome to write. But once when we discretize further, we will be in a position to obtain linear algebraic solution in a very comfortable way. Okay, one such form is Burger's equation. What is that historical perspective? Friends, two mathematicians, also they can be called as the physicists, they are even involved with the area of physics, Burger and Bateman. Okay, Harry Bateman and Johannes Burger, they were responsible in developing this form of equation, which is very popularly called Burger-Bateman equation. Okay, in a finite difference, saying what is the idea? We are in a position to structure or furnish the simpler form of linear algebraic equation. That is what the idea in CFD. Okay, we are coming across Laplace equation. Next, we have come across convection diffusion equation. What is the next one? It is Burger's equation. Fine. So, in a finite difference scheme, what is the next topic to be learned? Friends, there is a simple topic called implicit and explicit methods. Okay? In the 5 modules of computational fluid dynamics, starting from introduction, governing equations, next Euler's equation, representation of functions on a computer, finite difference, finite volume methods. These are the 5 topics to be learned for the undergraduate level. Among those 5 modules, this finite difference scheme is strongly emphasized. You should be in a position to know the information comprehensively. Okay? So, implicit and explicit methods, what are they? They are one of the ways in obtaining, once again, a simpler form of linear algebraic equation. Please bear in mind, you should be in a position to properly distinguish implicit and explicit forms. Okay? So, these are all the very small topics what you need to come across in learning finite difference scheme. Okay. So when we go in the advanced level, for each and everything we have to write the mathematical versions in a very esoteric way or a cumbersome way. But for the students of Bachelor of Engineering, they should be knowing the information to the surface level. That is very important. Okay, after knowing implicit and explicit forms, what is the next idea? Friends, in one of the previous videos, I clearly mentioned that to know about finite difference and finite volume methods, you should be aware of Taylor series expansion. Okay, when we take up any numerical or illustrative problem, at any point of time we will be in a position to use Taylor's expansion. So, whatever you have come across in engineering mathematics while learning Taylor series or Maclaurin's expansion, whatever you have come across, please recap the fundamentals so that you can have the stronger emphasis in finite difference scheme. Okay, so most of the things we are in a position to understand. Still more, we have few topics to be encumbered. What is the next idea? After knowing about implicit and explicit methods, there is a topic called successive over relaxation. Okay, you know that for any human being, relaxation or entertainment is very important. For our best friend, finite difference scheme, there is one topic which will rejuvenate or invigorate that scheme is successive over relaxation, which is abbreviated as SOR. What is that actually? In the examination or in the assessment, they may ask to write an explanatory or short note on successive over relaxation. What is that? Friends, let me tell in a very simple or an epigrammatic way. Successive over relaxation is one of the variants for Gauss-Seidel method. Okay, please bear that in mind. Okay, while learning linear algebra in engineering mathematics, first or second year engineering curriculum belonging to any university, pertaining to any university, students have come across about linear algebra. There, two prominent techniques, 2 to 3 prominent techniques, namely Jacobi's iterative method or Jacobi's matrix version, next Gauss-Seidel method, next Gaussian elimination. So these techniques they have come across. So when they are aware of those ideas, they can comfortably correlate in computational fluid dynamics. So what is that? SOR, successive over relaxation, is one of the variants for what? Learning Gauss-Seidel method. Anyhow, in the undergraduation level, students will learn about the theoretical ideas comprehensively. In the advanced computational fluid dynamics, students will learn about the problem solving techniques. Okay, but in the surface level, please remember this information. But what is the historical idea? Dear friends, successive over relaxation, this idea or technique was formulated by 4 people. Okay, let me tell their names. David M. Young, that is the first person who was responsible in initiating the idea of successive over relaxation. Next, Frankel, Phillips Frankel, he was the next person to initiate the action. Next to Louis Fry Richardson. Okay. Lastly, Southwell. Okay. Dr. Richard Wynne Southwell. So these 4 people were responsible in formulating the idea of successive over relaxation. If you know that technique, definitely you will be in a position to know about Jacobi's iterative method and Gauss-Seidel method. So at this point I am emphasizing that whatever students have come across in learning engineering mathematics, they have to recapitulate Gauss-Seidel method, Gaussian elimination, and finally Jacobi iterative method. Okay, so whatever problem you solve in a finite difference method, you will be in a position to understand very elegantly. Okay, all right. Let me tell about one or two lines about Jacobi's matrix and Jacobi's iterative method. Why the name Jacobi? Yes, it is named after a German mathematician Carl Gustav Jacob Jacobi. Okay, it is very lengthy, but please bear in mind these mathematical techniques you should be in a position to properly understand. Okay, they are all iterative methods. Whatever numerical problems you have solved in linear algebra, if you just revise it, you will be in a position to correlate with computational fluid dynamics. So friends, when you know about successive over relaxation, you will be in a position to get the idea about Jacobi's iterative method, Gauss-Seidel method. Is this all in a finite difference method? Friends, two more topics you should be aware of, 2 to 3 more topics. What is the next one? In the assessment, definitely your beloved professors will ask you to furnish information about TDMA. What is the acronym for TDMA? Friends, in any of the syllabus of computational fluid dynamics pertaining to any Indian or abroad university, TDMA is very important. What is the TDMA? The acronym is Tri-Diagonal Matrix Algorithm. Let me repeat, what is the acronym for TDMA? Tri-Diagonal Matrix Algorithm. What is this actually? Anyhow, you can furnish pages together the information pertaining to TDMA, but we should be in a position to know the information in a precise way. In a line, what can I tell about TDMA? Tri-diagonal matrix algorithm is the method of Gaussian elimination to identify the tri-diagonal elements in a particular system. Okay, let me repeat in a very simple way. Tri-diagonal, that means to say in a system we find tri-diagonal elements. So in a line, what can we tell? Tri-diagonal matrix algorithm is a procedure wherein we can take up Gaussian elimination technique. Gaussian elimination to identify what? Tri-diagonal elements in a particular system. Okay, this is also called Thomas algorithm. So this particular algorithm was initiated by Leavenworth Heath Thomas. Okay, in the assessment sometimes purposefully they may not ask, write an explanatory note on Thomas algorithm. Many students will be in the state of confusion or they will be obfuscated. Friends, please remember the other name given for TDMA, tri-diagonal matrix algorithm, is what? Thomas algorithm. Okay, it is a simple matrix technique. Okay, so here you will be having a matrix. In the second column you have the elements. Finally you have to solve that. Okay, so solving problems for the UG level may not be very essential, but for the advanced learning of CFD, solving problems on TDMA is very important. Okay, so this is a very prominent algorithm based on Gaussian elimination technique. Alright, okay, I have told about Thomas algorithm. The penultimate topic what you need to be aware is von Neumann stability criterion or von Neumann stability analysis. Okay, alright, let me tell few lines about this. While learning computer programming, I think majority may have come across the name von Neumann architecture or von Neumann architecture or nomenclature. Okay, very preferably. While learning computational fluid dynamics, or heat transfer. Students have come across three boundary conditions. What are they? First boundary condition basically temperature, next heat flux, the third one is convection boundary coefficient. But what are the three specific names for those boundary conditions? Number one is it is Dirichlet boundary condition. Second one is Newman boundary condition. Third one is David boundary condition. We are bothered about what? Von Neumann stability criterion. Von Neumann, anyhow, it is for the second boundary condition. Alright. Anyhow, in learning conventional heat transfer, what is that? Boundary condition of the second kind. Have you not come across about heat flux? The same idea. Okay. But in von Neumann stability criterion or stability analysis, what are we strongly relying on? Friends, von Neumann stability criterion strongly focus on the stability analysis of finite difference scheme. We will check the stability of finite difference scheme. This von Neumann stability criterion is also referred to as Fourier stability criterion. They are all interconnected. Friends, in one of the prominent videos, I have clearly told that whatever topics you learn in conventional heat transfer, finite element method, those two courses, you have stronger correlation or significance over computational heat transfer and fluid flow. Okay, so after knowing about tridiagonal matrix algorithm, you should be aware about von Neumann stability criterion. The last topic. Anyhow, while knowing about finite volume method, in the introductory aspect I have told, the three prominent schemes one has to be aware of. What are those three prominent schemes? One is the upwind scheme, second one is the central scheme, the third one, very important, Crank-Nicolson scheme. Okay, named after John Crank and Phyllis Nicholson. Phyllis Nicholson was a lady who initiated one of the techniques in finite difference scheme. Okay, but very prominently students should be aware about upwind scheme and central scheme. Okay, anyhow, in the video of finite volume method, while telling about central scheme, I have revealed three techniques. What are those? McCormack theory. The second one, Lax-Friedrichs method. The third one, Lax-Wendorf method. What order can we go? Lax-Friedrichs, Lax-Wendorf, McCormack. While learning upwind scheme, have you not come across flux splitting vector, Steger and warming, Van Leer, Rose method? Okay. So those names one has to popularly remember it. They have to very commonly remember those names while learning finite volume. When we get the connectivity in finite difference, the comprehension will be very easy for you. Okay. This is all the information one has to know in finite difference scheme pertaining to undergraduation level. Okay. I think whatever information I have furnished, it may be fathomable. For the sake of convenience or simplicity, let me quickly run through whatever information we have collected or agglomerated in finite difference scheme. Okay, let me quickly run through the information. Initially, a student should be aware about the need for finite difference method. Okay, what is the technique finite difference method? What are all the benefits, advantages and disadvantages and relevance in CFD? That is what they need to be aware. Also, in the introduction itself, better you try to know the differences between finite difference method and finite volume method. Okay, then it will be very easy for you to move further. Okay, what is the next topic we have come across? Yes, you are right. Relevance of Laplace equation in CFD. Next, you should be aware about the importance of convection diffusion equation. Okay, the combination of both convection and diffusion we will learn in finite difference scheme. Okay, so what is the next idea? Burger's Bateman equation. Okay, all right. One more mathematical term. Let me tell you in Burger's equation. Okay, I have told that it is possible for us to convert ordinary or partial differential equation into simpler form of linear algebraic solution. You will ask me, what is that Burger's Bateman equation? Very simple. You consider a field u of x comma t. U is a coordinate or it may be a velocity term. X is the direction, t is the time constraint. When you consider the field u of x comma t, then what will be Burger's Bateman equation? Very simple. Del u by del t plus u of del u by del x equal to nu del square x by del u square by del x square. That is all Burger's equation. Let me repeat it. Let me tell the essence of Burger's equation. While writing Burger's equation, you should be aware of the velocity term u. It can also be called a coordinate. When you consider the coordinate u, time constraint is very important. Why? Because sometimes we may go for unsteady state. Okay? Then along with u, x and t, we have nu. What is that nu? You remember thermodynamics or fluid mechanics. What is that nu? It is kinematic viscosity. So friends, if in the examination, if the facilitator asks you to write Burger's equation, what is the form? Let me tell in a direct way. Del u by del t. Change in u with respect to time constraint plus u del u by del x. Okay, del u by del x meaning what? Along unidirection, which is equal to nu del square u by del x square. Second order derivative you have to introduce. So u is there, x is there, time is there, kinematic viscosity nu is there. This is Burger's Bateman equation. After learning this, what is the next one? You should be aware about implicit and explicit methods. Fine. Later, you should be aware of three forms in convection diffusion equation. This I have already covered in one of the videos. Let me strongly tell in finite difference scheme, you have come across the abbreviated forms FTBS, FTCS, FTFS, CTCS. What are those for? FTBS, what is that? First in time, back in space. What is FTCS? First in time, centered in space. What is CTCS? Centered in time, centered in space. Likewise, we have FTBS. First in time, back in space. So these four acronyms one should be aware of. In one of the videos I have covered this. So let me repeat. FTBS, FTCS, FTFS, CTCS. These four abbreviations you should be aware of. Okay. Later on, which are the other four topics we need to be aware of? You should be aware about a topic called successive over relaxation. What is that SOR? It is one of the variants for Gauss-Seidel method. Okay. Conversion of ordinary or partial differential equation into linear algebraic solution. That is our sole motto or objective. While learning finite difference scheme and finite volume scheme, please remember this mantra. Conversion of partial differential equation into linear form of algebraic equation. Okay. So in one of the books authored by Suhas V. Patankar, okay, is an Indian author, basically a professor from IIT, a book on computational heat transfer and fluid flow. He has told in a very, very simple way. Alright, at the end, let me tell you which are all the recommended textbooks or reference materials. Okay, after knowing about SOR, which was the next topic I could cover, please remember three methods in linear algebra. Which are those three? Number one is you should be aware about Gauss-Seidel iterative method. Which is the next one? You should be aware about what? Jacobi's iterative method. The third one, Gauss elimination technique. Please practice the problems in engineering mathematics pertaining to the topic linear algebra. You have already learned in first or second year engineering. Okay, please practice the same so that you will be in a position to cope up with the numerical problems in computational heat transfer and fluid flow. Okay, so three iterative methods you should be aware of. Penultimately, I told about TDMA. What is that? What is the acronym for TDMA? Tridiagonal matrix algorithm, also called what? Thomas algorithm. It is named after Leavenworth Harriet Thomas. Okay. What is that one line illustration for TDMA? It is one of the Gauss elimination technique wherein it is possible for us to identify tridiagonal elements in a system. You will get many more information pertaining to TDMA. But for UG level, you please remember the theoretical ideas, simple matrix form you write, and few information you can furnish. Okay. Lastly, I discussed about von Neumann stability criterion. Okay. Von Neumann or Fourier stability analysis. It will check the stability in finite difference scheme. Okay. There we strongly rely on the conversion of partial differential equations into linear algebraic equations. Eventually, two popular schemes one should be aware of. What are those two popular schemes? One is the central scheme, the second one is upwind scheme. Even we have many other. We have Crank and Nicholson scheme, then power law scheme, many more we have. But strongly or basically these two are very, very important. Okay. So this is what I wish to cover in this video. Lastly, you may ask which are all the suggested material for comprehensive learning or study. You will find lecture notes, very popular videos from IIT professors, and many text and reference books are available. Which are the popular books? You can refer a textbook authored by Computational Heat Transfer and Fluid Flow by Suhas V. Patankar. He has written in a very, very concise manner. Any layman will be in a position to understand. But if you wish to take up a few more advanced books, Computational Heat Transfer and Fluid Flow by T. Soundarajan and K. Muralidhar, that is really good. They have written in a very, very, very comprehensive way. Okay, if a professor has experience over 20 to 25 years, definitely you will be in a position to understand. So, in-depth comprehension, you will get it. Okay. Other than that, Tannehill, Fletcher and Anderson, that is a very reputed book. T.J. Chung. Then you have Malalasekara, a course on computational fluid dynamics by Malalasekara. That is also a very well written book. So other than that, you will find many study material pertaining to the learning of finite difference and finite volume methods. Okay. I think I have covered enough information about finite difference scheme. Thank you very much. If you wish to get more ideas, that is very advisable. Thank you all for giving me an opportunity in sharing the information. All the very best. Good luck.